So picking up where we left off on Monday, we had talked about how to find the empirical formula for a compound from its percent composition or from the masses of the elements. How do we figure out what the molecular formula is? Well, the molecular formula has to be a multiple of the empirical formula. The empirical formula is the lowest ratio. The molecular formula is the actual ratio of atoms in a molecule. So to find the molecular formula, we need one more piece of information. We need the molar mass of the compound. So the molar mass of the compound is going to be some multiple of the empirical mass of the compound. So the molecular formula is the empirical formula times some integer. We can find out what that n integer is by taking the molar mass and dividing it by the mass of the empirical formula. So that probably doesn't make a whole lot of sense. Let's do an example, and hopefully it'll be more obvious. So a compound has the empirical formula CH. So, 1-to-1 ratio of carbon to hydrogen. The molar mass is 78.11 grams per mole. What's the molecular formula? Well, if we just think about this, CH, carbon is about 12, hydrogen's about 1, the molar mass of that would be 13, right? So that can't possibly be the actual formula, because the actual formula has a mass of 78.11. So what we're going to do is we're going to calculate the formula mass. So for the empirical formula, we've got 1 carbon and 1 hydrogen. So that's 13.018. If that was the molecular formula, it would be that many grams per mole. We want to see how many times does that fit into 78. So that's using division. So we take the provided molar mass and divide by the mass of the formula, the empirical formula. So the units cancel out. .11 divided by 13.018. 6.0038. These numbers should come out to very nice whole numbers, okay? They won't be exact, but they should be very close. 6.0038 is very close to 6. So the integer here is 6. That's what we multiply all the subscripts in the empirical formula by. So one way to express that is we take Cn and we multiply it by 6. So the molecular formula is C6H6. Any questions? The molar mass of the compound would be determined experimentally by using a mass spectrometer. How do you get the other information for the empirical formula? We talked about, well, you take the element, you break it down into, you take the compound and break it into its elements. How do you do that? One method is combustion analysis. This works for certain compounds. It's especially useful for organic compounds containing carbon, hydrogen, and oxygen. You burn the compound, and it forms carbon dioxide and water. And we can measure how much carbon dioxide is formed, measure how much water is formed. All of the carbon that was in the original compound goes into the CO2. If we know the mass of CO2 formed, we can figure out how much carbon was in it and how much carbon was in the original compound. All the hydrogen goes into water. So we measure the mass of the water formed, and we can calculate the mass of hydrogen in the original compound. If there's oxygen, we find the mass of oxygen by subtraction. So you take this compound containing carbon, hydrogen, and oxygen, you burn it, the mass of the elements that show up in the products has to be equal to the mass of what you started with. So all of the carbon that's in the carbon dioxide plus the hydrogen that's in the water plus the oxygen that we can't measure is going to equal the original mass. So we do that one by difference. How do we trap these things? Well, here's an illustration. We take a furnace, we put the sample in there, they weigh the sample carefully, and you need to provide oxygen so that this can be burned. So that oxygen comes in here, we burn it in this furnace, and all the gaseous products go out through this opening here, and they pass through a series of tubes with compounds in them that will absorb the water and absorb the carbon dioxide that's formed. So we weigh the tube before we do the combustion, and you weigh the tube after you do the combustion. The difference, the increase in mass, is due to this compound in here absorbing water, and this compound absorbing CO2. And so then we can identify the mass of each of those that was formed. So here's an example problem. Upon combustion, a compound containing only carbon and hydrogen produced 1.60 grams of CO2 and 0.819 grams of water. Find the empirical formula of the compound. To find the empirical formula, we need the masses of each element. This one only has two elements, carbon and hydrogen. We know it made 1.60 grams of CO2. That's not the mass of carbon, that's the mass of CO2. We have to find the mass of carbon that is in 1.60 grams of CO2. So what we want to do is we want to take grams of CO2 and we want to get to grams of carbon. How are we going to do that? We need moles, right? So using the molar mass of CO2, we can get 2 moles of carbon dioxide. By looking at the formula, we know the mole ratio. There's 1 mole of carbon in every mole of CO2, so we can get 2 moles of carbon. Didn't leave enough space. And then using the molar mass of carbon, we can get to the mass of carbon. Now, when you're actually doing this in a lab, you set up a spreadsheet with the calculations so that you don't have to do all these calculations over and over again. But we need the practice. 1.60 grams of CO2. 3 arrows, 3 factors. Grams of CO2 to moles of CO2 to moles of carbon to grams of carbon. Then we put the units in there so they'll cancel out. The numbers we need are molar masses. We're going to need the periodic table for that. And this mole ratio comes from looking at the formula. CO2, in every 1 molecule of CO2, there's 1 atom of carbon. So in 1 mole of CO2, there's 1 mole of carbon. Molar mass of carbon is just sitting there on the periodic table, 12.01. Molar mass of CO2 is the mass of carbon plus twice the mass of oxygen. That comes out to be 44.01. So 1.6 divided by 44.01 times 1 divided by 1 times 12.01. So this is going to get us 0.4366. 3, 2 extras there, grams of carbon. Now, let's think about this. The instructions for finding the empirical formula said you start with grams of each element, and then what do? You convert it to moles. So we're going to take this and we're going to going to convert it back to moles of carbon by dividing by this number. We could save ourselves a step, couldn't we? What if we just stopped here at moles of carbon? Then we wouldn't have to convert to grams and then convert from grams right back to moles. Everybody okay with that? You can certainly do this. Find the mass, and then take the mass and convert to moles and do the ratio. That is absolutely fine. I don't feel like doing that. So we're just going to stop right there. So we're going to stop here at moles of carbon because that's what we really need. So the moles, correct me if I'm wrong, but I think it's 0.036355. Did I get that wrong or right? It's okay. It's more fun to tell me I'm wrong. Moles of carbon. So then we're going to do a very similar process with the mass of water. 0.819 grams of water. We need to go to moles of water, and then we can go to moles of hydrogen, and then let's just stop there because that's what we ultimately want is moles of hydrogen. So grams of water down here, moles of water down there. How many moles of hydrogen in 1 mole of water? 2. The formula tells us that. And then here, right here, we need the molar mass of water, 18.016, 2 times the mass of hydrogen plus the mass of oxygen. So 0.819. divided by 18.016 times 2. So this gives me 0.0909. And I want to include at least 2 extra digits there, moles of hydrogen. Any questions? So now we've got moles of carbon, moles of hydrogen. What do? We need a ratio, right? So we divide by the smallest. The smallest one is 0.03. This one. So that gives us a ratio of 1. And this one, oops. Gives me a ratio of 2.5009. Is that a good formula? CH 2.5. No. Can we round it up to 3? No. We need to multiply. So let's try 2. If I multiply this by 2, I get 5. 5.0017. That is within 0.1 of a whole number, so that's 5. If I multiply the first one or the second one by 2, I have to multiply all of them by 2 to keep the ratio the same. So what I've got is a ratio of 2 to 5. So I've got C2H5. That's my empirical formula. Any questions? Are we going to do the molecular formula? If I remember, that's going to come up on a slide coming up, but I can't yet because I don't know what the actual molar mass is. Without knowing the actual molar mass, I can't find the molecular formula. Here's another one. Upon combustion, a 0.8009 gram sample of a compound containing only carbon, hydrogen, and oxygen produced 1.600 grams CO2, 0.6551 grams water. Find the empirical formula of the compound. That previous one was just carbon and hydrogen. This one also has oxygen in it. So this mass is including all the mass of carbon that was in the original sample, plus oxygen from burning it in an atmospheric containing oxygen. This mass of water has all the hydrogen that was in the original sample, plus oxygen. So here we do need the masses of carbon and hydrogen so that we can find out how much oxygen was present. The mass of oxygen will be the original mass of sample minus the carbon and minus the hydrogen. Okay. So 1.6004 grams of CO2. I'm going to convert that to moles of CO2. I'm skipping all the thinking it through part because we just did all of that. What I'm going to do here is I'm going to pull out an answer for my moles of carbon, but I also need the mass of carbon, so I have to multiply by 12.01 grams of carbon per mole of carbon. So 1.6004 divided by 44.01 times 1 equals, so, got lost here, that's 0.036364, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The sig figs are going to go away eventually, but we want to make sure we keep plenty. So that's moles of carbon. And then if I multiply by 12.01, that will give me the mass of carbon. I need the mass of carbon so I can find the mass of the oxygen. Grams of carbon. Any questions? I'm going to do something very similar with the hydrogen for water. The water for hydrogen. Oh my goodness. Spent several hours, many hours actually, on a bus with a bunch of elementary school students yesterday, and I think something happened to my brain. They can talk and talk and talk and talk. So I'm going to convert my mass of water to moles of water, and then I'm going to go to moles of hydrogen. And here the ratio is 2 to 1. There's 2 moles of hydrogen. That's a 1. There are 2 moles of hydrogen for every 1 mole of water. I'm going to need mass of hydrogen, but I'm also going to pull out the moles of hydrogen. 0.6551 divided by 18.02 times 2. That's going to give me my moles of hydrogen, 0.727. 0.8102. That's moles of hydrogen. And then if I multiply by 1.008, that gives me grams of hydrogen, 0.07329 grams of hydrogen. Hope that's not too confusing. I need to know about the other element, the oxygen. So for the oxygen, I'm going to take my original mass of 0.8009 grams of compound. I'm going to subtract the mass of carbon, 0.436737, and I'm going to subtract the mass of hydrogen. .8009 minus 0.436737 minus 0.07329. Grams. That's the mass of oxygen. Where would the last significant digit be in that number? It'd be the 4th decimal place. Here we're subtracting. This had 4 decimal places. This one, I didn't really mark it, but this one had at least 4. And this one had more than 4. I'm sorry, this one. So when I do this subtraction, my last sig fig is right there. I need to take that mass of oxygen and convert it into moles so I can do a ratio. So 16 grams of oxygen is 1 mole of oxygen. So I take that value and I divide by 16. 0.0181 796 moles of oxygen. I need to take all of these moles and divide by the smallest number of moles. Which element has the smallest number of moles here? The oxygen. So I'm going to divide oxygen by itself. Oh, the tedium of it all. That's 1. I'm going to take, I didn't leave any space. Moles of hydrogen divided by the moles of oxygen. That comes out to 3.999. That looks promising. And then this one, the moles of carbon divided by the moles of oxygen. Ah. 0.3636446, and that comes out to 2 with 3 zeros. So I've got this one, and I've got this one, and I've got that one. All of those can be rounded to whole numbers. This is the subscript for carbon. This rounded to 4 is the subscript for hydrogen, and 1 is the subscript for oxygen. We need a spot to write our answer. Carbon C2, H4O. That's our empirical formula. Any questions? It's a bit tedious, isn't it?